Okay, let's take another look at graphing motion, and we'll do it by analyzing a couple of graphs. So let's look at a couple of position versus time graphs, and we're just going to go very general. We don't even need to put any numbers on these. We'll just go by general shapes. So we have position on the y-axis, time on the x-axis, and let's start with, say, a line that goes like that, and another line going this way. And on the other graph, we'll have two lines going downwards. There's one line, and here will be the other. Now, recall a few things about these position time graphs. First of all, and really importantly, the slope of a position time graph, is going to equal the velocity, right? Because the slope is change in the y-axis or change in position over change in the x-axis or change in time, which is the definition of velocity. Okay, so the slope of a position time graph is velocity. A positive slope means you have a positive velocity, which means your direction, the direction of motion, is positive. Whereas a negative slope means you're going in the negative direction, or your velocity is negative. All four lines that I've drawn are straight. Remember that a straight line on a position time graph means your velocity is not changing. Why? Because in a straight line, the slope never changes. If the slope never changes, that means the velocity never changes. So a straight line is an indicator of uniform motion, or a velocity that's not changing. And finally, the steepness of the line is what indicates the speed. So the steeper the line is, or the steeper your slope is, that means the faster you're going. Steeper means faster. So with all that being said, with these position time graphs, can we translate those into velocity versus time graphs? So we're dealing with the same object in each case, but on the lines above, we're looking at its position versus time. What does its graph of velocity versus time look like? Let's start with the graph on the left. So we have a red line and a green line. Notice that they're both sloping upwards. That means their direction, or their velocity, is going to be positive because they both have positive slopes. Now, which one has a steeper slope? The green line has a steeper slope, so the green line has the bigger velocity. So let's say the green line's here. Now, why did I draw a straight horizontal green line? Well, because a straight line on the position time graph means your velocity isn't changing. A straight line on the velocity time graph, like say if this line here on the y-axis was 5 meters per second, that means your motion is staying at 5 meters per second. You're always going 5 meters per second. You're not changing your velocity. How about the red line? Red line should be the same thing because it's a straight line, so it has uniform velocity. Its velocity doesn't change. But notice that its slope is less steep or flatter than the green line. If it's less steep, then the magnitude of velocity, or the speed, is going slower. So we'll have our line about here. So if, say, the green line was 5 meters per second, the red line would be around 2.5 meters per second. Give yourself some time to see if you can do the same translation for the graph on the right. So see if you can take those blue and purple lines and of the position time graph and graph them as a velocity time graph. The way I think about it is, again, I see straight lines, so I know I'm dealing with uniform motion. which means my velocity is not going to change. I look at the slope, and for both those lines, the slope is downwards. So therefore the velocity should be negative. Where are negative numbers? They're down in this area of the graph, right? So if I look at the purple line, I see that it's flatter or has less of a slope, or it's less steep, that is, than the blue line. So it has less magnitude, or it's slower than the blue line, the object described by the blue line. So let's say that's my position time graph there. Actually, I should start it here. And for the blue line, it's steeper, so it should have a bigger negative number because it's going faster, just in the opposite direction than the object in the purple line. So my velocity time graph would look like this. Now I understand this can be a bit confusing, so before moving on to the next section of the lesson, I invite you to rewatch this first 6 minutes or so and see if that gives you a better understanding. Okay, let's do the same thing for a couple of other graphs, but we're going to change it up a little bit. So we'll start with position time graphs again. Position on the y-axis, time on the x-axis. And we're going to do that. We're going to do the same thing we did before, which was translate those position time graphs into velocity time graphs. This time, instead of straight lines, we're going to be looking at curved lines. Okay, so let's have a upward curving line like that, and a downward curving line like that. And I can extend those position time graphs a little bit. Now, remember, we're not dealing with straight lines here. So what does that curve mean? Well, in a curved line, that means your slope is changing. So you no longer have a constant slope. Your slope is changing. Well, if your slope changing, that means in the position time graph that your velocity is changing. So if slope of a position time graph is velocity and your slope is changing, that means your velocity must be changing. To look at this idea of changing slopes, let's take a look at the slopes at certain points along our graphs. Okay, so I have 6 points along that position time graph, and what I'm going to do is look at the slope of a tangent line to that graph. And a tangent line is simply a line that just touches a curve only at one point, but not at any other point. It never crosses the line again. It just touches the line. It just touches the line once. So if I look at the slopes of those tangent lines, you can see that I go from left to right, I go from a steep slope to a gradually more flat slope. So you can see my velocity should be fast, and then as the slopes go slower or flatter, then the object is going slower. And I can do it for the next 3. Flat, steeper, steepest. So you can see that the slopes are changing, or the velocity in this case, because it's a position time graph, the velocity is changing. Now, how would that graph translate to a velocity time graph? Well, if I look at those 6 points, starting from the left, the tangent line here is a pretty steep slope, and it's a slope that goes downwards. It's in the negative direction. So my velocity would be a big negative number. So say at that point my velocity is around there. The second point, the slope is steep, but it has flattened. It's still in the negative direction, so this is just a less negative number, let's call it. And when you're getting flatter, then your slope is closer to 0, or you're going really slow, but this slope is still negative. So you're close to 0 in the negative direction. For the point right after it, you're still flat, so your velocity is close to 0, but this time you're going in a positive direction. You're sloping upwards. So flat, but in the positive direction. That point should be around here. Next point, a bigger number for velocity, so you're going faster in the positive direction. And then the last point, very fast in the positive direction. So you'll come up with something that looks like a straight line as a velocity time graph, but one in which you go from a negative direction to a positive direction. So you're going fast in the negative direction, slowing down, hitting a velocity of 0. That's a velocity equaling 0. And then you're speeding up or going faster in the other direction. So you're going fast, slowing down, changing direction, and then speeding up again. And just know that whenever you change direction, you hit a velocity of 0. You stop for an instant. So when you change direction, you stop for an instant, your velocity is 0 at the point which you change direction. So velocity is 0 when you're changing direction. In this case, going from a negative direction to a positive direction. I know that could be a lot to take in, but why not try it for the other graph? Okay, just take a few points along the graph. Look at the slopes of the tangent lines. And you'll notice that you're going from a steep slope to a flatter slope, and then a flatter slope to a steeper slope. So again, you're going faster and then slowing down and then faster. And if you look at the direction, your slope is upwards and then your slope goes downwards. So you're changing direction at that middle point right there. So over here, if I look at my points, I'm going from a steep slope in the positive direction. I am changing direction, which means my velocity is going to be 0. And then I speed up again to get to a steep slope or a fast velocity in the negative direction. So my velocity time graph is going to look like that. So a couple of points about these graphs. The curved line on a position time graph, so I'll specify curved line on a position time graph, means the slope is changing, therefore the velocity is changing. A straight line on a velocity time graph, so velocity time. Straight line on a velocity time graph means that your velocity is changing. So that means that velocity is changing. What does it mean to change velocity over a certain period of time? That sounds a lot like acceleration. So your velocity is changing, therefore that object is accelerating. So a line with a slope on a velocity time graph means the object is undergoing acceleration. And we can go even further. We can say that the slope of a velocity time graph equals acceleration. So let's see. The slope we know is rise over run, or change in y over change in x. In this case, what is the y-axis? The y-axis is your velocity. So change in y is actually change in velocity. X-axis is time, so the change in x is actually change in time, or the time interval. And we know that equation. Change in velocity over time interval equals acceleration. That's the definition. So the slope of a velocity time graph, slope of velocity time graph equals acceleration. So I want to revisit these 4 graphs, and I want you to think about 3 things as you look through these. I want you to think about the velocity, in particular the direction. Is the velocity going in the positive or negative direction? Acceleration, same. Is acceleration going in the positive or negative direction? And speed or magnitude of velocity. Is the object speeding up or is the object slowing down? So if you'd like, pause the video, think about those three main things for each of the graphs and see if you can figure that out. If not, I'll just go ahead and do it right now. As for velocity, so if I look at these graphs, and I'm going to split them each down the middle because that's where there's changes to all this. If I look on the left side of the graphs on the left, that is, I know that the velocity in these cases are in the negative direction. Why? Because position time shows negative slopes, or it's sloping downwards, which is a negative velocity. Also, if I look at the velocity time graph, this whole area here is negative, right? So the velocity time graph shows this whole area is in a negative territory. So velocity is negative. The opposite true is true for the other half. So the other half we're going positive. All of this area of the graph is in positive territory. All the slopes on that part of the graph are sloping upwards, which is a positive velocity. So velocity is negative in one half of the graph, positive in the other. Going by similar logic, on the green and blue graphs, we have positive velocity, which then goes to negative velocity. As far as acceleration, now remember, acceleration is the slope of the velocity time graph. So we can see from the velocity time graph, this is sloping upwards, which means a positive slope, which means a positive acceleration. So acceleration is positive for the whole graph. For the green and blue graph, for the velocity time graph, we see a downward slope. If slope is acceleration and we have a downward slope, that means our acceleration is negative. Negative and negative. Now, when are the objects speeding up or slowing down? As velocity gets close to 0, right? As velocity gets close to 0, that means it's slowing down. Further away from 0, it's speeding up. So we go far away from 0, or a big negative number, to 0, that means we're slowing down. But on the other part of the graph, we go from 0 to a high number for velocity, that means we're speeding up. On the other graph, we're heading towards 0 for our velocity number, towards 0, so we're slowing down. And then for the other part, we're getting a bigger and bigger number for velocity as time goes on, so we're speeding up. This leads to a couple of important points. Number 1, a curved line on a position time graph means acceleration is occurring. That means you do not have uniform motion. Your velocity is changing. Also, if the curve is open or the curve is upwards, say the curve is pointing upwards, upwards curve means positive acceleration. Then the downward curve, downward opening curve, means negative acceleration, right? The green position, in the green position time graph, the curve opens downwards, and we can see our acceleration is negative. On the red position time graph, the curve opens upwards, and our acceleration is positive in those cases. Now I want you to look and find the cases where we're speeding up. And we are speeding up here. What does that tell you? Look at the direction of velocity and direction of acceleration. So when acceleration and velocity are in the same direction, then you are speeding up. You're going faster. The opposite is true if velocity is negative, acceleration is positive, or velocity is positive, acceleration is negative. So when acceleration and velocity are in different directions, you slow down. Okay, let's take another look at velocity time graphs for one more important point that we need to make. So I'm going to draw two more graphs. And again, these are just velocity time graphs. And we'll put a touch more detail in this. This is going to be velocity in meters per second going in the east direction. Meters per second going east. And in our first graph, we have an object that is going 5 meters per second from 0 to 10 seconds. And for our other graph, it will also end up at 5 meters per second after 10 seconds, but the object is going to start at a velocity of 0 seconds, so its graph, I should make it a straight line, looks like that. So broadly speaking, what's the difference between the two graphs? Well, let's call this graph A, and the graph on the right, graph B. And graph A shows a horizontal line, graph B shows a sloping line. Well, the slope of a velocity time graph we know is acceleration. So if your slope is 0 in a velocity time graph, meaning your line is horizontal, then that means your acceleration also equals 0. Not that your velocity equals 0. Okay, that can be confusing. If graph A was a position time graph, then a flat horizontal line would mean you're stopped, you're not moving. But this isn't position time, this is velocity time. And in a velocity time graph, the flat line just means you're going at a constant velocity. You're going 5 meters per second throughout this whole 10 seconds. You're always at 5 meters per second. So it's not that your velocity is 0, it's that your acceleration is 0, which means your velocity is not changing, aka you're undergoing uniform motion. And the other major piece besides the slope of a velocity time graph that you can garner is what we call the area under the curve. So the area under the curve, which is the area between the line in your graph and the x-axis, the area under the curve equals the displacement of the object. And let's look at graphs A and B, for example. So for graph A here, if I want to calculate the displacement is the area under the curve. And if I look at this shape, so the area under the curve is between the line and the x-axis. So I want all of this area here. That just looks like a rectangle, right? A rectangle with length of 5 and a width of t, or a length of the velocity times the width of the time. We know velocity times time is displacement. Okay, so again, area under the curve, this is a rectangle. The width is 5 meters per second. We multiply that by the width of 10 seconds. So the displacement is just a positive 50 meters, a positive 50 meters, and a positive means you're going in the east direction. So the displacement for your first graph is the area under the curve, which is 50 meters per second to the east. For graph B, if you wanted to get information on the displacement, well, the displacement is the area under the curve, the area between your line and the x-axis, so all of this, and that's a triangle. What's the area of a triangle? The height of the triangle times the base of the triangle divided by 2. So your height of the triangle is also 5 meters per second. The base of the triangle is the 10 seconds. So 5 times 10, and then you divide by 2. That equals 25 meters. It's a positive 25, so you're going 25 meters to the east. Okay, so a decent amount in this lesson about going over graphs. A couple of the main ideas are if you see a curved line on a position time graph, that means your velocity is changing. That means your object is undergoing acceleration. In a velocity time graph, if you have a sloping line, a straight sloping line, that means that your velocity is changing, and the slope of that line equals acceleration. If you have a flat horizontal line on a velocity time graph, that means your slope is 0, which means your acceleration is 0, which means you're undergoing uniform motion. I'll post some homework and some homework solutions online for you guys to try out. And again, if you have any questions, please feel free to email me or jump onto those online tutorials. Thank you.